Hi everyone, my name is Kyle Damborsky. I'm a graduate student at Texas A&M University and I'm part of the NSF GK through 12 program. And I'm going to be coming into y'all's classroom and helping y'all out with a little bit of your science this semester, this year. I'm a third year graduate student in the Department of Physics and I'm working on a PhD in applied physics, which we'll talk about what exactly that is in a little bit. But how I ended up getting to A&M was I graduated from high school back in 2003 from Industrial High School. It's a small school, I think we're 2A, that's not that far from Victoria, Texas. After that I went and did my undergraduate degree at Tulane University and spent 4 years there, and that's in New Orleans, so it was a lot of fun. And now, back in Texas at A&M. So, like I said, I'm in the Department of Physics and I'm working on a PhD in applied physics. But what that actually means, what I actually do, is I work on superconducting accelerator magnets. The superconducting accelerator magnets that we work on go into very big science experiments like the LHC, the Large Hadron Collider, which is starting up this year over in Europe. The accelerator magnets, what they do is they bend charged particles that are going very, very close to the speed of light so that they can travel in a ring and then collide with one another. And then scientists use detectors and different things to study these collisions to actually find out what protons are made out of. And you can use these to probe the most fundamental, smallest building blocks of nature that we know of so far, and you can find new and exciting ones, which hopefully that's what's going to happen at the LHC. Probably a little more familiar application of what I do would be MRI machines. All MRI machines built today use, or most of them, use superconducting magnets, which these are magnets made out of superconducting wires that are very, very efficient and very, very good for creating magnetic fields. The reason you use superconductors are, unlike normal copper or a regular conductor, superconductors carry a lot of current at very low temperatures. And there are a lot of really interesting things, interesting phenomena that come about because of superconductors. There are a lot of really cool properties to them, and there are a lot of really useful ones. And most of my work focuses on using those properties of superconductors and technology. So a little bit about how I actually got interested in science. You're probably wondering how a guy from South Texas, went to a small school a lot like yours, ended up working on accelerator magnets and trying to get involved with these massive science projects. Well, I've always been really interested in science. Whenever I was 5 or 6, I used to go out in the yard, collect bugs, lizards, anything like that, just try and classify them and see what made them unique. And I always loved math, and whenever I got to high school, I really, really enjoyed chemistry, and my chemistry teacher, which is probably the reason that I'm in physics now, we were studying the orbital electrons of an atom and how the transitions between different energy levels creates light. It's something that we'll talk about this year, probably in the spring, but it's one of these amazing phenomena, and it's just absolutely blew my mind whenever I discovered that, whenever my teacher taught me that. And after that, I've been doing physics ever since, and I can't imagine doing anything else right now. And hopefully I can get y'all excited about this as well. There's a lot of really cool stuff in physics and chemistry and just science in general, and I really hope that y'all can see some of that this year. Well, instead of keeping talking about what I actually do and how what my research is about, I'm going to take y'all out and show y'all around at our lab, which is probably going to look a little bit different than what you expect a physics laboratory to look like. So come on, and I'll show y'all around. Hi, so we're in the conference room out here at our lab, and on the wall we have the designs for a few of our magnets. What's unique about the magnets that we make out here is the stress management that goes into the cables. For example, whenever you cut these magnets on, there are loads and loads of stress, and there are lots of forces that act outward on the cables that we're using to make these. To manage that and to keep these cables just from ripping each other apart, the designers out here have come up with a really great way of supporting the windings. So that's kind of what makes us unique. And if you look over at this magnet here, the outside of this is all just structured to try and hold in the magnet, to hold all the forces in and to keep the thing from ripping itself apart. Inside the little green area right here, that's actually where a proton is going to travel eventually. That's what we're hoping, at least. And then we have little superconductor windings all the way around them. And those are what carry the current that creates the magnetic field that bends our charged particles as we go into the accelerator. Alright, so this is actually where the magnet is going to go eventually. This is an aluminum shell where we've got that's wrapped around our magnet that keeps everything in place, and it acts like a rubber band holding all the pressure in. This is an iron yoke that we have that is used to return some of the flux from the magnet, and in the center here, that's where our superconducting windings are going to go eventually, and that's going to be the meat of the actual magnet, and that's going to be where all of our magnetic field is going to be coming from. Alright, so we're interested in creating really, really high magnetic fields, and that takes a lot of current. And it's not really the same as the current going through the wires in your house or anything like that. Those are very, very small currents compared to what we're talking about. For instance, this is a copper cable that we use to carry the current that goes into our superconducting magnet. Now this material is a lot like the wiring that's in your house. It'll carry about the same amount of current as what's going in your house. Each one of these little filaments will. It's a little bit bigger, right? So it carries a lot more current than anything that your house probably has, but it's the same material. It carries the same per square inch, basically. Now what I've got in my hand, this is a superconductor. Now this thin little strip will carry about the same amount of current as this big thick cable that's right next to it. And that's why we use this in a magnet, because this small little cable can carry enough current to actually get us our high field in a really, really small area, which is that's the most important aspect of a superconductor that we're going to be using in our magnets. So, when you think of a science lab, you probably think of some people running around in white lab coats with, beakers and small equipment. You don't really think of an industrial-sized warehouse, which is where we do most of our work. And we're set up out here to do just about anything that you can imagine, especially when it comes to metal in our magnets. Alright, so now that you've seen all the pieces that go into making a magnet, what do you actually get whenever you finish one up? It's actually something that looks a lot like this. This little centerpiece is where the electron or where the proton beam goes, and all these little dark spots here, that's actually superconductors. And that's where our current goes, and that's what creates the magnetic field that we're looking for. This is actually pretty much solid metal, and then inside of it, it's got a little bit of epoxy. That should be just an open hole. But this is just a sliced up piece that we use to go back and look at what our magnet actually looks like. So that's it. That's what we're trying to build, and looking forward to getting through with one of these pretty soon. Alright, so we got one more piece of equipment that's kind of fun to play with, and this is a dry argon glove box. So what you basically do is stick your arms in the gloves, and it allows you to work in an atmosphere that doesn't have any oxygen or any water in it. And this is really important because some of the powders that we have on these shelves will actually ignite if they come into contact with air or just oxygen. So it's very important that we keep that safe and dry and oxygen free. Well, this is lab, and this is my office where I spend most of my time whenever I'm not out on the floor doing something. But now that you've seen where I work, I'm going to take you home and show you what I do whenever I've got some free time. So come on, and let's go see what's going on at my house. Alright, so whenever I'm off work, I spend a lot of time at my house where my lovely wife Joanne, who's filming this, and I have been since May. It's our first house, so I've been really excited about it, and been doing a whole lot around here. So come on inside, and let me introduce you to the other two members of our family. So like I said, I'm married, and my wife is also a graduate student in the Department of Neuroscience. So whenever we have free time together, we like to spend it doing things that we can do together. And usually that means we watch a lot of movies. We are both pretty big sports fans, and actually we're looking forward to football season starting up here. And we've started doing a little bit of fishing just to spend a little bit more time together. Aside from that, we spend a lot of time with our cats, and the newest one is Athena right here, who we've had for about 3 months now, and oh, she's a wriggler. And our big boy Herm on the floor, who is getting used to having a little sister still. Well, I'm really excited about meeting y'all, and I can't wait for this semester and this year to start up. I hope y'all are excited, and we're going to have a lot of fun and hopefully learn a lot about physics and chemistry this year. So I'm looking forward to it, and I'll see y'all soon. Bye.